increase. This is definitely a fully nonlinear problem, which are tackling from a numerical point of view. So let's start with the, oh, no worries. Yeah, but this doesn't work. I can do it from here. No worries. Oh, okay, good. So let's start with the linearized model. In the linear regime, we consider, like I said, small amplitude waves. So here the primes indicate physical variables. A prime is the amplitude of the incident wave. Lambda prime is the wavelength of the incident wave, which we take as a reference for the length scale. And of course, this ratio is the nonlinearity parameter. In other words, the steepness of the wave, which we assume to be much smaller than 1. W prime, well, of course, K prime is the wave number. W prime is the width of the flap. So we can define then a characteristic parameter, which is the product between K prime and W prime. And looking back at the literature, when we started to analyze this problem, we could see that there was quite a lot of studies in the small case. So when regime, when K prime W prime is much smaller than 1, it means the device is very small as compared to the characteristic wavelength. And this is called the point absorber theory, which is very celebrated and dates back to the 1970s. And then on the other end of the spectrum, we have the case where this K prime W prime is much greater than 1. So essentially the device behaves almost, it's called a terminator. So it's a two-dimensional device, which is essentially parallel along the wave crest. And again, we could find quite a lot of references in the two-dimensional case, most importantly by Professor May at MIT. But there was almost nothing in the intermediate case, which it's important because it's really the way, the regime where these devices operate. So where KW is of the order 1. And therefore, we have to consider in this case a full three-dimensional diffraction radiation problem in fully dispersive waves. So that's what we did. This is something, like I said, I did quite some time ago, so I will go very quickly. This is at the basis, of course, of the nonlinear results that I will show you later. So we consider linear potential flow theory. In other words, we assume that the fluid is inviscid and incompressible. The flow is irrotational. This is the geometry of the system. So this is a top view, and this is a section of the device. And in linear potential flow theory, this means that we have a velocity potential, which satisfies the Laplace equation in the fluid domain, plus a kinematic dynamic boundary condition on the free surface, and a flux condition on the seabed. So we are considering that the seabed is flat and is impermeable to water. And then this is the most important condition, is the most challenging one, is the kinematic condition on the flap, which says that the normal component of the velocity field on the flap has to be equal to the velocity of the normal velocity of the flap itself along the x-axis. And here, to solve this problem, we've considered an approach which was derived by Chris Linton and Phil McIver. It's called the thin plate approximation. So what we do is we neglect essentially the thickness of the plate, considering that in normal applications, this thickness is of the order of the meter, whereas the width of the flap is of the order of tens of meters. Yeah. No worries. Yeah. Yeah. Yeah, thanks. This is a really good question. Yeah, in these models, we've considered a rigid flap. We are now studying the problem with flexible devices, which introduces much more complexity, because in that case, yeah, you can have also the essentially some resonances due to the fact that the shape of the flap can change. Yeah. But for today, I will show you only the results for a rigid flap. So we are considering that normally the width of the flap is of the order of the meter. The main dimension of the flap, so this W prime, the width is around 20 to 30 meters. So these are really giant flaps, and the wavelength is around 60 to 100 meters. So essentially, this very tiny dimension can be neglected, And so we consider that the flap is thin, and using this device, we can get, first we non-dimensionalize variables, separate time, I mean, this is usual procedures, decompose the potential into incident, diffracted, and radiative wave fields, and we solve them separately, and then we combine them all together. And very quickly, we did this with a semi-analytical working scheme using Green's integral theorem. But today, I will also show you some more, some newer results in which we hopefully find a much easier method, and we didn't have to use the Green's integral theorem. So I'm just reporting this for completeness, but the method that I will use for the nonlinear problem will be different. So I will start again from the linearized problem using a different method of solution. But just to show you some of the results, we validated this linearized model with respect to experiments that we had in the lab. So this is the wave torque with respect to the frequency of the incident wave. We can see that we have very good agreement between the model and the experiments. And in particular, also given the fact that there is a difference between the model flap and the experimental flap, because in the experiments, you can see that the flap is not flat, but it's made by cylinders. But actually, this small deviation from it being a flat surface does not affect the linearized results. I will show you later that, in fact, mathematically, these effects of the small curvature of the flap enter at the second order. We had also very good the opportunity to take numerical comparisons. And again, we have very good agreement with the numerics as well. And then we did some parametric analysis on this. Now, I want to move on the weakly nonlinear regime because it's definitely more interesting. So now we are moving to essentially consider the second order effect. And we also wanted to analyze the shape effect. So at this point now, we are also considering the fact that the device can also be different from having a rectangular shape. So we're considering that the flap can have a curvature in both the horizontal plane and the vertical plane. So here you can see, and we also consider arrays. So we also want to investigate what happens when we have a series of flaps all working together, so more than one flap. In this plot here, you can see this is a top view. So the wave is incident at a given angle psi. So we're also considering inclined incidents, non-orthogonal incidents. The array is organized along the y prime axis. The total width of the array is w prime. The width of each of the devices that compose the array is a prime. And here is a vertical cross section, where again, we can see that now we have a shape function delta prime, which is normally non-zero, and that can change along the y prime direction and also the vertical direction. So here we have the usual nonlinearity parameter. Now we assume that this is smaller than 1 and its square is much smaller than 1. So we do not consider cubic nonlinearities. We've then extended also this to cubic nonlinearities with multiple with a multiple scale approach, and it's in the papers that I will mention later on. But today I will not show you this, the analysis at the third order. I will stop at the second order, and then we also define this shape parameter mu. Now, when we consider the flap shape function, which is the deviation of the shape from it being a simple rectangle in the section, in the cross section, we consider that this deviation is of the order of the meter. So essentially, mu is comparable to the nonlinearity parameter. So the shape parameter and the linearity parameter have essentially the same scale. And we will see that in weakly nonlinear regimes, this deviation, this curvature of the flap, will have an influence on the power output of the device, which doesn't happen in the linear case. So here are our governing equations. This is the reference that we've published 3 years ago now with my postdoc. So these are the governing equations. Again, we have the Laplacian of phi equals 0. We are already now in non-dimensional variables. So the premise disappeared because we've non-dimensionalized everything. This is the dynamic condition, the kinematic dynamic condition on the free surface. So zeta is the free surface, g is the non-dimensionalized gravity. So in terms of non-dimensionalization, we take lambda prime to be our scale for the length, and omega prime is the frequency of the incident wave to be our scale for the frequency. And in this particular case, this study, we consider monochromatic incident waves. We've also expanded this to irregular waves. Of course, we also still have the no flux condition on the seabed. And then the boundary condition on the flap now is much more complicated because we have the effect of the nonlinear terms and the shape terms. So epsilon, just to summarize, is the nonlinear term, and mu is the shape term. So of course, in the limit, as epsilon and mu both go to 0, we recover the linearized theory. Otherwise, of course, now we have to expand this in Taylor series with respect to the linearized equilibrium position, and then we get the problem at the different orders. And of course, we have the equation of motion of the qth flap. So each flap is independent on the others, and it has to, its motion is governed by this equation. So we have one such equation for each flap, where we have, this is essentially Newton's law. So this is the moment of inertia, the term essentially given by the angular acceleration. This term is, this is again gravity, this is the buoyancy term, and this is the power takeoff. So essentially this is modeling the fact that we are now using a generator to extract energy from the device. So this force that the power takeoff imparts on the device is proportional to the angular speed of rotation of the flap. And on the right-hand side, yeah, we have the wave torque. And again, we can see that in the wave torque, we have the nonlinear effects and also the shape effects again. How do we solve this? We found a way to solve it analytically. So in the previous example with the linearized approach, I showed you a mixed semi-analytical model where we used the Green theorem and used then a numerical approximation. In this case, the solution is purely analytical, so we did it in a different way. We assume a perturbation expansion of the physical quantities. So all the physical quantities are expanded into a regular perturbation series. So phi, for example, the velocity potential has its first order component and then the second order, and we stop at the second order. So we only consider quadratic nonlinearities. And then, of course, we can keep expanding. And like I said, we've also done a further study on this to consider cubic nonlinearities. And of course, given the fact that we have wave-wave interaction at the different orders, this generates higher order harmonics. So each of these terms is then phi 1 and phi 2, and also the same for all the other quantities, is then expanded into a harmonic series at the different orders. So starting from 0th harmonic up to, of course, the second harmonic at the second order. And the idea is that when we plug all this decomposition back into all the equations I showed you before, then we are able to decompose the problem into a cascade of linear boundary value problems at each order n and harmonic m, and then we solve them, and then we put everything back together. So this is an example. In general, what we have for each order n and harmonic m is again the Laplace equation. And then we have boundary conditions. This is the dynamic boundary condition, and this is the kinematic boundary condition on the free surface. And then again, the bottom boundary condition, of course, is always linear. And then we have the condition on the surface of the array, plus, of course, the equation of motion for each flap. And at the different orders, these are forcing terms. So for example, at the second order, these terms include the first order forcing on the second order solution at the different harmonics. We solve this for each harmonic and at each order using this analytical method. So we transform our system into elliptical coordinates, where chi and theta are the new coordinates, and w is again the width of the entire array. And then it turns out that with some calculations, we are able to express the solutions in terms of material functions. I've just reported, for example, the first order solution, but a similar solution can be found also at higher orders. So this is the first order solution, including the cosine Mathieu function, the sine Mathieu function, and the this is the Hankel-Mathieu function, the even Hankel-Mathieu function, and this is the odd Hankel-Mathieu function. The second order solution is much longer, but it's the same idea. So we have a series of Mathieu functions. Now let me show you some results that we've got. So first of all, of course, when we consider higher order nonlinearities, we have the emergence of subharmonics, in particular the zeroth harmonic, which essentially means it doesn't depend on time. And this is because when we combine waves at the first order, we have terms e to the I omega t times e to the minus I omega t, which gives us something that doesn't depend on time. And what happens, so therefore, with the zeroth harmonic is that we have a drift force, and of course we know it. And because of this drift force, the angle of rotation of the flap is inclined. So the neutral position of the flap in the linearized model is essentially vertical, and the flap oscillates like this. But because of this nonlinear contribution, so the zeroth harmonic, instead it oscillates like this. So the neutral position of the flap is inclined, and this is the angle of inclination with respect to the frequency of the wave. So this is a parametric analysis, and for two particular cases. So this is normal incidence, and this is oblique incidence. And we can see that we have several peaks. So in this particular cases, the flap oscillates with respect to an inclined axis. In particular, this is more pronounced for normal incidence. And now let's move to the wave energy extraction. So what is the nonlinear effect on wave energy production? These are plots of the capture factor with respect to the frequency of the incident waves. Capture factor is a measure for efficiency. So it's the ratio between the extracted power and the incident wave, the wave flux per unit width. So it's essentially a non-dimensional measure of efficiency. It's not hydrodynamic efficiency, so it can be higher than 1, and you can see it here. And this is because the device, when CF is higher than 1, essentially the device is also extracting energy from the sides, okay? If this was a purely two-dimensional system, then CF would correspond to the hydrodynamic efficiency. But in 3D, this can be also greater than 1. And this is plotted for several configurations. So the dark bold line here is the flat configuration. And then we have several configurations, this delta 1, delta 2, they correspond to different geometries. I've only reported here these two shapes, number 4, delta 4, which is this continuous line here, and delta 6, which is the dotted line, because they are the most promising ones. So what happens because of nonlinearity? Well, of course, we have a large peak, and this is the linear peak. It's the linear resonance peak that we also have in the linear theory. Then in the linear model, this curve would go gently to 0. So because of nonlinearity, we have a secondary, I wouldn't call it resonance, I would say amplification of the capture factor. This is because of essentially the presence of the bound wave at the second order. At the first harmonic, that's the one that generates this. In particular, this is more pronounced with these two configurations. So it looks like when we have concave configurations, we have a secondary peak at large frequencies, which is particularly useful, for example, if we are in basins like, for example, the Mediterranean, where we have waves around the 2 or 3 radians per second. So in that case, I mean, the nonlinear effects and the shape effects will combine to give us a secondary sort of peak of energy. And interestingly, this doesn't happen for the inclined case. So when we have inclined incidents, then essentially we don't have anything here. So this only works for normal resonance. We believe that this is essentially because of the focusing effect. So this acts almost as like a lens, and it focuses energy near the flap, which can be extracted then. So now let's move to the array. So all this analysis was for a single flap. Now we also include the effect of the array. So here we consider what we call a 5-flap array or a finger flap array. So instead of considering a single flap like we did before, we cut it into 5 small flaps. each of which have, their own width is 1/5 of the original flap. So the total width of the system is the same as before, but it's cut into 5 flaps, which are totally independent, so they can oscillate as they like. We can see that in this case, the effect of the second order drift is again that it creates, it generates an angle θ2 0. So it's, again, due to the fact that because of the second order drift, the neutral position of these flaps can be inclined. And interestingly, when we have oblique incidents, this can be pretty important. But most importantly, in terms of wave power capture, what happens is something really interesting, especially for the inclined incidents, oblique incidents. So again, for the configuration delta 4 and delta 6 that I showed you before, again, we have a similar behavior. We have this is the linear resonant peak. Then we have a second peak here. And we believe this is because of the articulation of the device, which introduces other essentially relatively local peaks. And then again, another peak here, which is due to the combination of nonlinear shape and also array effects. But what is really interesting is that now we have the same, another peak for the oblique incidents, which before we didn't have. If you remember the plot before, for the single device, this went to 0 very quickly. So the articulation of the system now produces a secondary peak here at relatively higher frequencies. So to conclude, I showed you that in a rise regime, the device is not affected by shape effects, if that, of course, they are of the order of the wave amplitude. In the weakly nonlinear regime, we have the emergence of a second order drift, which changes the neutral position of the flap, so it doesn't oscillate any longer with respect to the vertical axis, but it oscillates with respect to an inclined axis. And also it affects all these nonlinear and shape effects affect the capture factor of the device. In particular, I showed you that engineering or designing the device in a way that it's essentially concave, this determines a 20% increase of the capture factor at larger frequencies, and that this is only possible in normal incidents with a single flap, but this also becomes possible in oblique incidents with a finger flap. So it looks like essentially using the same width, but cutting the device so that it behaves as a system of articulated system of devices, actually can increase the power capture in obliques. And that's all. So these are the references. And thank you very much for your attention. Okay, that's away from my
Merrick Shrokos from the National Oceanography Centre in Southampton. Nice to see stuff on wave power. That's where I started my career in the 1970s. What I was curious about was, I wasn't clear from your presentation whether these flaps were submerged or surface piercing. And if they are surface piercing or submerged, does that make a difference to the power extraction?
Yeah, thank you very much. This is a really good question. Yeah, the analysis we did is for surface piercing flap. So we were working mostly with Aquamarine Power, which was a company based in Scotland, and they had a patent for surface piercing flaps. We've also done some analysis for submerged flaps, though only linear, and it looks like already at the linearized order, the power capture is less than surface piercing flap, essentially because energy decreases with exponentially as you move towards the seabed. So yeah. Yes. Yeah.
Cool. Yes. Have you considered doing shape optimization, where you actually solve for the shape?
Yeah, not yet. That's a really good question. Yeah, this is something we have in mind, and in this case, I think using machine learning probably would be really useful because in that there's been some work by a group in Sweden on this. So they've used machine learning not really for shape optimization. I mean, in the way we've done it here. So I think combining their approach with this approach would be useful because, you know, with machine learning, you could essentially study many different configurations in a much faster way than just doing it by hand, essentially giving different shapes for this delta. Yeah. So you, essentially, in that case, you find a target function, which is your energy, and you have to optimize it by changing this parameter delta. Yeah.
So question, in the show region, you have usually wave breaking, so the vorticity is generated. How to include the vorticity in your model? Because potential flow maybe is not always a good model.
So this is for, I mean, in most of the time, these devices operate in weakly, linear to weakly nonlinear waves. So in most of their life, they are designed to operate in sort of gentle waves. So in that case, the linearized, well, the potential flow approach works well. Of course, there are cases where you can have extreme waves. In that case, it's really different. So there are some of these devices that are designed to essentially move into a non-operational position when we have extreme waves. So they just move to the bottom and they survive these waves in that way. There are other devices that cannot do that. And in particular, the oyster was not designed to move into a idle position. So in that case, of course, you have to consider vorticity, you have to consider highly nonlinear effects. And for that, I mean, I think, well, I'm not aware of any analytical or semi-analytical solution. In that case, it's pretty much numerical work.
More questions? Well, I have a question, short question. So in one of the slides, I mean, wait, this conclusion slides. Conclude.
Oh, sorry.
Yeah. So optimizing configuration to some extent will be it provides a 20% increase in capture factor at large frequencies. Yeah. So, but what would be the overall voltage increase of the overall power capture? I mean, well, not just from large frequencies, but overall.
In that case, I mean, that depends on the wave climate. So depends in real life. I mean, the wave, the sea is not monochromatic, so we have a range of frequencies. So
basically, I'm saying I ask you how important this increase overall, because you increasing capture factor at large frequencies, but we are interested in capturing overall power.
Yeah, so it depends on where the device is. Probably, you know, if the device is in the North Atlantic, so the main resonance, which is around, you know, the 10 seconds, which is already a relatively large period, but in the North Atlantic, you can get something around, you know, that, so waves around that period, 7 to 10 seconds. So this secondary resonance is not important, but if you move to smaller basins, so in particular, we've done this study with an Italian company that are trying to develop this for the Adriatic Sea. In that case, you don't have in the Adriatic, you know, you have 3-4 second waves. So in that case, it becomes important. So it really depends on, because in the Adriatic, you will not capture or Mediterranean, you will not capture the first resonance at 12 seconds because you don't have any energy there. But this increase in capture factor for the smaller frequency, the higher frequencies, so the smaller periods, can be determinant in that case for the device to be able to extract something. I mean, of course, it's not comparable to what you could have in the North Atlantic, but still, it's doable, it's viable in that case. Yeah.
Yes. Thank you. Yeah. Yes, sure.
What is important for you? Is it energy or power? I mean, maybe higher omega gives a larger power, although you cannot extract much of it.
Yeah, I mean, what we calculate is power. Yeah.
Okay.
More questions? Okay, let's thank our speaker again. Thanks, Emiliano. And now we have lunch break, and we are back at 1:45. No, 2. Okay, 2 o'clock. We move. Okay, more time for lunch. Thank you.